Einstein Fellow at Berkeley, and did his doctoral work at Harvard. He's worked on everything from reionization to semantics of Ostriker effect to lemon alpha forest to building out haze. And today he'll tell us more about methods to attempt reionization.
Thank you so much for having me. So I'd first just like to thank my collaborators. In particular, a lot of the original research I'm going to discuss was done in collaboration with Ryan and O'Leary. I'd also like to acknowledge the two Epoch of Relonization and high redshift 21 centimeter efforts that I'm involved with, Paper and Lita, and others who might have worked with on 21 centimeter projects in the past. And so if we were to take all of the images we've compiled over the years in various wavebands with various telescopes and put them into a photo album chronicling the universe's lifetime, then we would have a few pages dedicated to the infancy of the universe, especially around the universe's 375,000th birthday, the time that we see the CMB originating from. And even though these pages would be few in number, they would illustrate in vivid detail what our infant universe looks like, getting a Gaussian random field, seeded with scalar variant potential fluctuations at its 375th birthday, 10 to the minus 3 fluctuations in the dark matter. However, the vast majority of our pages would be dedicated to the adulthood of the universe. And essentially, everything that we observe that's not the primordial CMB anisotropies, I would throw in this category. Even our deepest observations with the Hubble Space Telescope, where we're able to see galaxies, even a bit further back than when the universe was 1 billion years old, we see accumulations of tens of millions of stars, so very nonlinear, evolved objects. And so by the time the universe turned 1 billion, the simple Gaussian field had transitioned to this much more complex, nonlinear environment. And we all know that by 14 billion years, there's just this rich and complex phenomenology of stuff in our universe that we make a living studying. And so this talk is about filling in the missing pages. And so there's a transition from these small fluctuations, Gaussian field, to this much more complex place. And our best hope for really getting detailed pictures of this epoch is with high redshift 21 centimeter. And so just to motivate things a bit further, let me provide 3 more motivations for why 21 centimeter pictures could be particularly interesting. And so the first motivation is, I claim that 21 centimeter is really the only method that we know of that's capable of directly studying the first operating regions. Even our future space telescope, the James Webb Space Telescope, will only be sensitive to accumulations of hundreds of thousands and millions of stars. Whereas, as I'll show you, 21 centimeter is potentially sensitive to more diminutive stellar populations that we think exist in the early universe. And the second motivation is that 21 centimeter constrains the thermal history of the universe at an interesting time. And so the red curve is just a toy model for what the temperature history of the universe after redshift 1000 could look like. And this model has been constrained at low redshifts with a line alpha forest. And there are essentially no surprises there. We find that the IGM has a temperature of order 10,000 Kelvin, which is basically what you expect from photoionized gas. The universe after redshift 16, after redshift 6, redshift lower than 6 is photoionized, and so no surprises. At very high redshifts, we know that we know the CMB temperature, and because there's just so much energy in the CMB, we know that the baryons must have been thermally coupled to the CMB just by collisions, sort of like cont scattering. And we think that this coupling should be efficient down to about redshifts of a couple hundred. And at redshifts lower than a couple hundred, these Compton collisions are no longer efficient enough to keep the gas coupled to the CMB, and the gas starts to cool adiabatically below the temperature of the CMB. And this adiabatic cooling precedes until the first sources turn on, produce X-ray and ionizing photons, and latches onto the lower redshift protonized IgM that we see in the Dynamical force. However, if the IgM is able to cool to, for example, by redshift 20, it would cool, if the sources hadn't heated up the universe, it would cool to 10 Kelvin. And if the IgM is able to cool to 10 Kelvin, this actually leads to a whopping 21 centimeter signal. And so 21 centimeter is potentially, and I'll describe the physics in a few minutes, sensitive to the temperature of the universe over this interesting range where the IgM is getting very cold. And then final motivation is that when we finally take pictures of the universe with 21 centimeter, the pictures may look totally different than what we're anticipating. And so what this shows is the power spectrum of 21 centimeter fluctuations. It's just a measure of how the brightness temperature fluctuates on a range of scales. And so an old prediction for what the 21 centimeter signal should look like, and this is redshift 20, are that it should look like this red curve, tracing the density fluctuations in the universe. But recently, it has been realized that there actually might be another piece of physics that our old models have been missing that could cause the 21 centimeter signal to, rather than look like this red curve, look like this green curve. And if it looks like the green curve, then not only would it be much easier to detect, it's much larger. K of 0.1 is roughly the scale that instruments are most sensitive to. But you would have these distinctive acoustic oscillations, and then I'll describe why at the end of this talk. And so if the signal looked like the screen curve, it would be really exciting. Okay, so those are the motivations. And so the outline of this talk is I'm first going to give an introduction to high redshift 21 centimeter radiation. I know that there are a lot of people familiar with the physics, but just so that we're all up to speed. And then I'm going to summarize different efforts that are going after the signal. And then finally, and the bulk of this talk is going to be some new theoretical progress regarding what the signal could look like at different times. So as we all know, this is a hyperfine transition of hydrogen between the electron and the nucleus, the proton. And as you change the frequency that you're looking at to observe this signal, then you're looking at different redshifts. And so lower frequencies equal higher redshift. And so this means that in contrast to the CMB, where you're only observing one surface, you can measure a three-dimensional space and do tomography and map the universe as different processes are happening, map the universe as a function of redshift. And I claim that if we want to study the IgM at redshift greater than 8, then this is really the only line that was of primordial origin, that was produced in the Big Bang, that we can really use to study the intergalactic medium. Basically, every other line is either just way too weak or too saturated. For example, the Lyman alpha line of hydrogen, which we've used a lot to study the low redshift IgM, is no good for studying the IgM above redshift 5 or so, or 5 or 6. Things are just becoming way too saturated. And so the fundamental observable is the brightness temperature contrast with respect to the CMB. And the brightness temperatures that you're looking for range from of order minus a couple hundred millikelvin to 30 millikelvin. Negative brightness temperatures mean that the transition is absorbing the CMB. And the principal challenge with detecting 21 centimeter is that you're trying to detect this small millikelvin signal on top of a sky, which is hundreds of Kelvin. And the sky temperature is coming from foreground emission, synchrotron and Brunstrom radiation, a lot of which is coming from our galaxy. And the only reason we think that we can separate the signal from the sky is that all of these processes are continuum processes. And so if you just take all of the contaminating emission, and so if you just take an electron, a single electron that's radiating synchrotron or Brunstrom radiation, then its spectrum is smoother in frequency than the structure that we're looking for in this 21 centimeter signal, just for a single electron. And so what we think we should be able to do is we'll measure the signal as a function of frequency and then just spit out a smooth function and isolate the 21 centimeter signal. In practice, it's difficult, and a lot of people here are involved with, trying to do this exercise. So again, you observe the brightness temperature contrast with respect to the CMB. And the brightness temperature contrast depends, of course, on the neutral fraction of the gas. It's emission from neutral gas. Depends on the density of the gas, and it depends on something called the spin temperature, which is just a measure of how your number density in the excited state to the ground state of the hyperfine system. And you can show that the spin temperature is basically related to all of the other temperatures in the universe at the time you're observing the signal. And so if you don't have anything pumping your 21 centimeter line, the spin temperature is equal to the CMB temperature, and that means the brightness temperature is zero. There's nothing you can observe. There's no contrast. However, you can have collisions pump your 21 centimeter transition. You just have two hydrogen atoms collide, and they can exchange spin. And that drives your spin temperature to the temperature of the gas with a coupling coefficient that depends on the density of the universe. And so at high redshifts, when the universe is very dense, the gas temperature is coupled to the spin temperature. This is redshift. However, around redshift 40, the universe is no longer dense enough for these collisions to be effective, and the spin temperature converges to the CMB temperature. And it would be made at the CMB temperature for all time, unless you had something else that could pump the line. And so however, there is something else that can pump the 21 centimeter line, which is UV radiation from stars. And so stars will radiate UV photons, and they'll redshift into the Lyman resonances of hydrogen. And most important is the Lyman alpha resonance. And you can show that this couples your spin temperature to the color temperature of the radiation with a coupling coefficient that depends on the intensity at the Lyman alpha resonance. And then the final ingredient that you should know is that the color temperature of the radiation is effectively the temperature of the gas, because a Lyman alpha photon will scatter of order 1 million times as it redshifts through the resonance of hydrogen, and these scatterings impart energy. And you can easily show that the color temperature of the radiation then converges to the temperature of the gas. This is called the Wüthuysen field effect. And so all pumping processes drive you away from the CMB temperature and to the temperature of the gas. And so that's why 21 centimeter is sensitive to the temperature of the gas in the universe. And so when your first stars turn on, they produce these UV photons, and this recouples your spin temperature to the gas temperature. And it actually takes very few photons, that redshift in the Lyman alpha for this coupling to be effective because these photons scatter so much. And then your first stars also heat up the universe. And so in terms of what you observe, the brightness temperature contrast with respect to the CMB, when the first stars form, you generically get a dip into absorption. And there are a couple instruments that I'll discuss that are going after this dip. And then when you have enough stars form that you can ionize the universe, you get rid of all your neutral hydrogen, and your signal goes away. And so most instruments are going after this signal from reionization, and this is the sky average signal here. But there are a class that are going after the signal from when the first stars form, because this signal can potentially be quite a bit brighter.
I don't understand how Lyman alpha photons affect this.
Yeah, so your Lyman alpha photon comes in, and your hydrogen atom is in the 1s state, and it takes you to the 2p. And then you emit a Lyman alpha photon, and you'll go back down to the 1s. But you also have the hyperfine state that you can go. You tend to go preferentially back into one of the hyperfine states because there are the quantum selection rules. And so if you work this out, you can show that because your radiation is taking you from one state, and when you scatter into the other state, then that this causes you to go, causes you to pump the line, and slightly more energetic photons have a higher probability of getting you into the excited state, and so that's why the color temperature of radiation matters. But the Wüthuysen field mechanism is somewhat complicated, and so if you're interested, I recommend this review by Perlin and Owen Briggs. Okay. So part 2, I'm just going to summarize the different observations that are going after the signal, and then I'll get to the research part of this talk. Okay, and it turns out that there are 2 types of observations. There's a class going after the fluctuating part of the signal, so looking for brightness temperature fluctuations in space. And then there's a class of instruments that are going after the signal from the whole sky. And it turns out that the design of these instruments are quite a bit different. And in terms of the instruments going after the fluctuating signal, it's really become a worldwide effort. And so there are many instruments that are going after the signal in a variety of continents. You guys, of course, are familiar with GMRT, which Wei-Li and his group has been involved with. Wei-Li also built 21 centimeter array. But in general, most of these instruments look like a bunch of dipoles in the field. They're not the prettiest instruments. The rough order of magnitude of the collecting area of these instruments is 1% of a square kilometer. So they're quite a bit smaller than the square kilometer area that we ultimately hope to have in this field. And in fact, 1% is an exaggeration. Some of these are closer to a 10th of a percent of a square kilometer. And it turns out that a 10th of a percent to 1% is basically what you need to be able to detect the signal and tend the signal. And so just to give you a sense for what, so the fluctuating efforts to this date are only going after the Epoch of Relonization signal. And so to give you a sense for what this signal looks like, I'm going to show you a movie from an old simulation of reionization that I ran, and it's in a 100 moving megaparsec region in the universe. It's a cosmological simulation. And when I start the movie, you'll start to see colored regions, which are the ionized regions. And then on the left, on the right panel, is the power spectrum of the 21 centimeter signal, which is what these instruments are going to observe. And the reason, for the first generation of instruments, you're not able to image the signal. On any pixel on the sky, your signal to noise is less than 1. And so for the first generation of detections, we hope to have a statistical detection of the signal. And the statistic that you're most sensitive to is the power spectrum of fluctuations. And so what you're going to see as reionization evolves in the simulation, the power spectrum is also going to evolve. And the game, when there's finally a detection, is to go from the measurements of this power spectrum and try to infer what is actually happening, what it means for the topology of the reionization process. And so this is just going to give you one illustration of how this happens. And just the assumptions in the simulation is that it's roughly dwarf galaxies of order 10 to the 9 solar mass galaxies that are ionizing the universe. Okay. So I'm starting the simulation. So initially, your first sources turn on, and they're ionizing the regions around them. The regions around them are the most overdense regions in the universe because the first sources are highly biased. And so the power spectrum initially goes down because you're getting rid of regions that have a lot of neutral hydrogen, dense regions. But eventually, because of the clustering of sources, you tend to get very large H2 regions during the reionization process and a range of scales. And so your 21 centimeter power spectrum tends to flatten, and then eventually goes away when you get rid of all of your neutral hydrogen. And so it's this type of evolution that you're going to observe with these 21 centimeter efforts, and from them you're going to try to infer what is going on with hydrogen reionization. The other class of instruments is rather than going after the fluctuations, is going after the average signal as a function of redshift. And so the instrument that has really excited this field is EDGES, which Jed Bowman and Alan Rogers pioneered. One thing you might notice is that these instruments look quite a bit different than the instruments that are going after the fluctuating signal. Rather than being thousands of dipoles in a field, these look like a single dipole. LIDA, which I'm involved with, is also just a couple of dipoles, although it's near the long wavelength array in New Mexico, which it uses to calibrate. But it's a couple of well-calibrated dipoles. And the reason a single dipole is sufficient is that it turns out that unlike for the fluctuating signal, for the signal from the full sky, you're statistically sensitive to the signal with an integration on a single dipole of order a couple hours. And so but the main challenge with the signal, the efforts going after the signal from the whole sky is that now that you're going after the signal from the whole sky, it doesn't have fluctuations in the function of frequency that are as large as if you were looking, in a skewer as a function of redshift. Where if you're looking in a skewer, you would have go in and out of individual H2 regions. If you're going over the whole sky, you're just averaging all of that out. And so you're hoping that the cosmological evolution in the signal is still faster than the evolution in the foreground. And for these instruments, also you want to understand the gain response of your instrument excellently, because if you don't understand the gain response, then you have an extra evolution in your signal that is not cosmological. And so in order to isolate the cosmological signal, you need an excellent understanding of your instrument. And so these are really well designed, well-calibrated dipoles that are going after the signal. And DARE, I know that Jack Burns was here recently and gave a synopsis of, and this is a small explorer mission that's been proposed and is still being proposed to go after the signal. Okay. And so, and this is my last introductory slide. I apologize if the introduction has been so long. But and so the signal that these instruments are going after, the signal from the full sky, looks like a dip when the first stars turn on, and then when reionization happens, you're getting rid of your neutral hydrogen. And so it is going after this transition from having a neutral universe to an ionized universe. But you can see that in frequency space, there's not a lot of structure that is expected. We expect that reionization takes an order of Hubble time. And so what that means in frequency is that the signal is spread out. And so it's unclear if you can separate this fairly smooth transition from the foregrounds. And so the new generation of instruments, LIDA and DARE, are going after this dip when the first stars turn on, because it seems much more promising that it looks different than the smooth foregrounds that you need to isolate it from. And what these different curves show are just different random parameterizations spanning a huge amount of parameter space for how the first ones produce Lyman alpha photons and X-ray photons. And you can see that in a lot of these models, this dip exists. So the current thinking is that this dip is pretty robust. Okay, so these experiments are racing to detect these signals. However, there are some open theoretical questions that I'm going to discuss that may impact their success, their design, and their strategies. And so the remainder of this talk is going to be focused on 3 questions that will pertain to all of these different types of equivalence in the experiment that I've discussed. And so first, I'm going to discuss what will we learn by observing the fluctuating 21 centimeter signal from reionization. What is this going to tell us about the reionization process? And so this is a very important question for these instruments that are going after the fluctuating signal from reionization. Secondly, I'm going to turn to this higher redshift global signal. And so, do shocks prevent the IGM from cooling sufficiently to yield a significant absorption trough in the sky of the signal? So this absorption trough that I've been showing you depends on, requires that the IGM cools to order 10 Kelvin. And there has been one numerical study in the past that finds that weak shocks start to heat up the intergalactic medium and prevent it from cooling adiabatically like you would assume in just a homogeneous calculation. And so if that happens, that's bad because the signal goes away. And so this would be analogous to, at redshift less than 1 in our universe, you start to get 100 kilometer per second convergent flows that shock heat the IGM to 10 to the 6 Kelvin, and you develop a hot phase for the intergalactic medium. However, when the IGM is 10 Kelvin, you just need a 0.3 kilometer per second flow to be supersonic. And so just very weak flows could potentially be shocking and heating up the universe and causing it to not cool adiabatically and erase the signal. And then finally, the last question is, do the supersonic velocity differences between the dark baryons and dark matter enhance the fluctuating signal from ionization? And so what are the supersonic velocity differences? Well, it was realized, and we've known for a long time, that the baryons were being dragged around by the CMV prior to recombination, and then at recombination, the CMV lets go and the baryons are coasting. And it was actually shown very recently that the baryons are actually coasting at a supersonic velocity relative to the dark matter. And so this, if you're able to couple your 21 centimeter fluctuations to these supersonic velocity differences, and I'll explain this in a bit, then you can really drastically enhance and change the character of your 21 centimeter signal. Okay, so what will we learn by observing the fluctuating 21 centimeter signal from reionization? Okay, so reionization is a very messy astrophysical process, but I would like to just first highlight what we know. And so what we know is we have a very well-tested model for the density structure of the intergalactic medium, at redshift 3 with the lemon forest especially, because we've really tested our cosmological simulations. And we also understand how halos cluster. And so this is what we know when we're modeling ionization. What don't we know? Well, there's a lot of astrophysical uncertainty. We think faint galaxies are responsible for ionizing the universe. However, which faint galaxies, we don't know. We don't know how ionizing photons escape out of galaxies. Presumably they are escaping the universe becomes ionized. The galaxies that we think ionize the universe are much smaller than the galaxies that we're seeing in the Hubble deep field. Or the escape of ionizing photons is very efficient out of the massive galaxies that we're seeing. Okay, so there's a lot of astrophysical uncertainty. And so I'm going to show you some ray tracing calculations on top of a cosmological simulation of what reionization looks like with various parameterizations for what the astrophysics, how the astrophysics may be happening at high redshifts. And so, but first let me just show you this panel, which is, this panel is just a 100 kelumen megaparsec slice through this simulation box. All of the simulations are showing you 100 kelumen megaparsecs. And I'm showing you a slice through a third, the width of the slice is a third of the simulation, so it's 30 megaparsecs. And I'm showing you 1% of the sources. And so you can see that there are a lot of sources. If I showed 100% of the sources, there would be several million sources in the simulation box. And if you look at these simulations of reionization, then it's really the clustering. It's very hard to see here, but the clustering of these galaxies that is shaping the large-scale structure of reionization. And so it's possible, because there are so many sources, that it's even though we have a lot of uncertainty in reionization, it's the clustering that is primarily determining the structure of this process. And I'll try to back this up a little bit more. Okay, and so what each of these each of these columns show is just a different mapping from the mass of halos in your simulation to their ionizing luminosity. And so here the ionizing luminosity scale is halo mass to the 1/3 power, and the smallest mass halos are of order 10 to the 8 mass, which is the atomic cooling threshold in these simulations. In this column, its luminosity scale is halo mass to the power 1, luminosity halo mass to the 5/3, and here halos above 10 to 10 solar masses. And this column roughly corresponds to if the largest halos that we observe in the Hubble deep field are ionizing the universe. And so, and each of these rows are the same ionized bracket and same redshift. We tune things so that ionization happens with the same history in these simulations. So one thing that you notice is that as more massive halos ionize the universe, the structures are larger. And the reason for this is because the more massive halos are more biased, they're more clustered. And so you have and the clustering is driving the structures of these H2 regions. And in fact, if you looked in one of these large H2 regions, there would be thousands or tens of thousands of sources. And it's the clustering that is really shaping how the topology that we're seeing. Okay, and so how does this relate to the observable? Well, what these 21 centimeter instruments are going to observe is the power spectrum of fluctuations. And so as you get larger bubbles, you have more power, more large-scale power in the 21 centimeter signal that these instruments are going after. And so these are distinguishable. However, there were a lot of there were other processes that we tried to parameterize that we found had less of an effect on the structure of reionization in the simulations. And so what these panels show are, again, 100 megaparsec slices. The white regions, again, are ionized regions. And roughly, we're at when the universe is half ionized in these simulations. And so these slices are showing different parameterizations for how, when you ionize a region, you suppress the low mass galaxies. Because when you ionize a gas, you raise the Jeans mass of the gas considerably. And so this suppresses accretion of gas onto 10B9 solar mass halos. And this process significantly delays reionization when we put it in the simulations. And so each of these are just a different parameterization. And so if we're given a maximal feedback case, we just shut off all of the halos below the Jeans mass of the gas from producing ionizing photons. And so reionization is significantly more extended in this case. But you can see that if you compare at the same ionized fraction, the structures are not significantly changed. And that's because we're not changing the clustering of the sources that much. We're on a part of the bias as a function of halo mass where the bias isn't changing very much, even though we're shutting off the low mass halos. And so the clustering, again, is driving the structure. And then another thing that we investigated is, let's say we make the sources 5 times more efficient than ionize the universe. So reionization happens at redshift 11 compared to redshift 8. If we again compare the same ionized fraction, then the structures look very similar. And that's because, again, the clustering isn't changing that much. And so our conclusion is that the 21 centimeter experiments that are targeting reionization teach us primarily about the clustering of the sources of ionizing photons that reionize the universe, in addition to the global reionization history. Okay, second question. Do structure formation shocks prevent the IGM from cooling sufficiently to yield a significant absorption trough in the sky average signal? As I mentioned, there has been one previous study of this by Gnedin Shaver in 2004. And what they found is that shocks were having a significant effect on this absorption trough. And so the dashed blue is their prediction when they suppress entropy generation in their simulation. So that when shocks happen, gas isn't heated up. And the magenta is the case where they're just doing the full hydro calculation, where entropy can be created in shocks. And you can see this dashed blue probably goes down to minus 100 millikelvin or so, although they don't see that. But you can see that the magenta differs significantly from the prediction where there are shocks. And if this dip is only minus 20 millikelvin, then that's really bad. This is 5 times more difficult to detect than minus 100 millikelvin. So we wanted to investigate whether this actually happens. And so to do this, we decided to run simulations that I claim are the most realistic simulations of the early universe. And so why do I say that? So it turns out actually that a lot of simulations of the early universe assume that the baryons trace the dark matter. This isn't true for all of them. But at redshift 100, the baryons and dark matter do not trace each other. In addition, our simulations are the first to include pressure and effective pressure on the growth of modes. And the rate of growth of modes in a consistent manner. This is typically neglected in how initial conditions are put down. We were the first to include temperature fluctuations in the gas, which are important at the gene scale of the gas, because the universe has inhomogeneous temperature fluctuations when you're starting a simulation at redshift 100. And basically the motivation of all of this is we know linear theory, so we might as well start off the simulations with linear theory, and people hadn't been doing this. And finally, ours are the first to include this velocity difference between the baryons and the dark matter in a consistent manner, where it's implemented consistently in linear theory. People had before, there have been only a few studies of this, but before they've just been taking normal transfer functions and just kicking the baryons, which is bad, because that will disrupt some of your potential wells in a more violent manner than they should be disrupted. Okay, and then in all of our simulations, we resolve routinely, sometimes with a lot of elements, or tens of thousands of elements. And we ran many simulations to test convergence, and we also ran Gnedin and INZO simulations to make sure that the simulations agree. These are just two cosmological codes with each other. Okay, so what did we find? Well, if we look at the mass average temperature, then the universe does start to heat up around redshift 20. Like there are shocks, especially in around halos with virialized regions, and the universe is heating up. However, if you weight in a manner that's more appropriate for 21 centimeter, which is closer to a volume average weighting than a mass average weighting, but it's not exactly a volume average weighting either, then we're finding that the heating is of order tens of percent. So this is Gnedin and INZO, and we've offset INZO just so that you can distinguish the two. And each of the curves are a different set of simulations, or simulations with different box sizes and resolutions that I'm not going to get into. But we find that the residuals of order 10%. So they don't qualitatively change this picture, and that the universe is able to cool to several Kelvin at redshift 15. And so our conclusion is that this should be there for these global experiments, that the universe isn't shock heating. And we think the reason for the discrepancy with Gnedin and Shaver is actually, it turns out that a lot of hydrocodes don't do very well at just the simple test of conserving entropy in a homogeneous expanding universe, whereas Gnedin and INZO do a very good job at that test. And INZO has a higher order accurate Riemann solver. Okay, and then finally, and this I think is the most interesting part of the talk, do the supersonic velocity differences between the baryons and dark matter enhance the fluctuating 21 centimeter signal? Okay, so just a bit of background on what these supersonic velocity differences are. Again, the baryons are moving with respect to the dark matter, and it turns out when the universe is cooling adiabatically, that on average the baryons have a Mach number of 2 relative to the dark matter. But like everything in cosmology, it's a Gaussian random field, and so the modulus of the velocity is a Maxwellian. The typical Mach number is 2. But in some regions in the universe, the Mach number is 4. In some regions, it's 1. And if you just plot what the power spectrum of this difference is, then you see these acoustic features, because it's the same acoustic physics that's shaping this difference that is giving you the acoustic oscillations in the CMB. And one thing that you should note to understand what I'm going to show is that on the scales of the simulation boxes I'm showing you, which are much smaller than the silk damping scale, which is the minimum correlation for this relative velocity, this relative velocity is essentially just a wind over the simulation box. There's no structure in it. Okay, so you can envision this coupling to the 21 centimeter signal in a multitude of ways. For example, it can homogeneously heat the IGM. You can have shocks in regions where there's a higher Mach number. You can have more shocking and heating. It also can suppress the formation of the first cosmic structures and the first stars. And it's the radiation background from the first stars that are heating up the universe and pumping the 21 centimeter line. And so if you modulate these, then you're introducing another source of fluctuations in the 21 centimeter signal if this velocity difference is modulating these processes. And so I'm going to first concentrate on the shock, inhomogeneous shock heating. And so it turns out that if you just couple a very small fraction of the energy in this relative velocity into shock heating in the universe, you could have an enormous 21 centimeter signal compared to what people have been predicting. So for example, if you thermalize just a few percent of this relative velocity, then your 21 centimeter signal would look like this green curve, plus the red curve. And the red curve is just what has been predicted in the past. A 21 centimeter signal that's tracing density fluctuation. And so your signal is going to be a superposition of these two terms. And so at large scales, and these are scales that are very, very observable, potentially very observable, then your signal could look quite a bit different if you were able to thermalize 3% of the energy in this relative velocity. If you were able to thermalize 1%, it would look like the blue curve. Okay, so here I'm just going to show you two movies of what that illustrate how the relative velocity suppresses small scale structure. These small scales that we see here, again, this is just a 0.3 co-moving megaparsec region in the universal small region, are not observable. You don't observe 0.3 co-moving megaparsec regions with 21 centimeter unless you had 10 times SKA size instrument. But what we're most interested in is how this couples with the long wavelength modes that are observable. But let me first show you how it is affecting the small scale modes. And so this is a simulation box where there is no relative velocity, and this is one which has a 2 sigma fluctuation in the relative velocity. So it's a relative velocity with a Mach number of 4. Okay, so I'm going to start the simulations. And they started at redshift 100 and they end at redshift 15. And you just can see that structure is quite a bit more filamentary. And we're looking at the density of the gas. Even at redshift 100, you can see that has had an effect. And by redshift 15, the power here is much more anisotropic than in the case of outer relative velocity. And so it's affecting the small scale structures. Your relative velocity is causing the gas to go in and out of small potential wells in the universe. And so I'm going to motivate why, and this was the motivation for why we started working on this. But motivate why you might expect that there is a large coupling to this relative velocity via inhomogeneous shock heating. And the motivation is just gaseous dynamical friction. And so it turns out that for Mach numbers of order 2, dynamical friction gaseous dynamical friction is very efficient. And so these are just curves from a paper on gaseous dynamical friction by Ostriker. And so what gaseous dynamical friction looks like is you have a point perturber, in our case a halo, or a region that's going down linear collapsing. And behind it, you get a Mach cone. This Mach cone is, you have shocks. The perturber is going through the medium, moving to the right in this case. And it's the mass in this cone that is decelerating your object and causing it to lose its velocity. And you can show that for a 10 to the 4 solar mass halo, which is a fairly small halo, that the dynamical friction time scale is the Hubble time at redshift 20. For a 10 to the 5 solar mass halo, it's a 10th of a Hubble time. And so halos are losing, the gas around halos is coming, the dark matter and the baryons are coming into the same frame via this process. And if this energy is thermalizing, then this could lead to large temperature inhomogeneities between different places in the universe. And in fact, if you just look at the simulations, you see this happening. So this is just a cut through the gadget simulation. The gas here is moving to the right. And you can see, if you look, like that there are a bunch of cones as the gas is traveling past your nonlinear structures in your simulation. And basically, we find that all of the overdense gas has come into the same frame as the dark matter via this process by redshift 20 in our simulation. And this plot just shows that. I'm not going to go into the different curves in this plot. And so do the associated shocks generated entropy and evac the 21 centimeter signal. If you were thermalizing all of this energy that's going into deceleration, then the answer would be yes, you would have very large fluctuations. And in fact, if you just look at the temperature-density relationship in the simulations, when you have this relative velocity, you get a lot more dispersion in your temperature-density relationship when you don't have anything that basically back. Okay, but the conclusion is kind of anticlimactic, which is that, so we ran a bunch of simulations and we figured out what the coupling is, and we find that at redshift 20 it's closer to this case, whereas this is the prediction for the old 21, the standard prediction for the 21 centimeter signal. It becomes a little larger than this by redshift 15 if the IGN is still able to cool to redshift 15 before the sources heat up the universe. But it's too bad, but that's how it worked out.
You said that in the boxes that it thermalized all the energy by redshift 20.
Oh, it didn't thermalize, but so the bulk motion was lost. Now, whether it's thermalizing and what densities it's thermalizing are the question. These are very weak shocks, and so so it seems like a lot of the motion is actually just it's still in kinetic energy, just more. It hasn't thermalized. But yeah, it was surprising to us that not more of it was thermalizing.
Wow. So you ran a number of Mach numbers, or?
Yeah, that's right.
And so then you average over them?
Yeah, so it's the variance that's showing the amplitude of these curves. And so we know the PDF of Mach numbers, and then we can kind of sample that with a bunch of simulations and compute what the variance is. And then the integral of this curve is equal to that variance. Okay, so that's too bad. That mechanism didn't work. And so now we're going to focus on how this relative velocity could affect the formation of the first stars and modulate the 21 centimeter signals via their radiation backgrounds. And so if you just go into these simulations and ask and look at halos that we think would host some of the first stars, then the accretion of these halos is affected by this relative velocity. So this is a several times 10 to the 6 solar mass halo. And again, the wind in this case is moving to the right. And you can see that this filament is not here in this case. And the mass within the virial radius of this halo is quite a bit lower. It's a order factor of 2 lower. And so the accretion of gas onto the halos that we think are forming the first stars is affected in these simulations. Here's another halo. And again, you see that I mean, here you have some kind of bow shock. And, I mean, the morphology is quite a bit different. And this is again a few times 10 to the 6. This is quite a bit larger than the 10 to the 5 solar mass halos that we think was the very first stars. But these halos are more robust, allowing Warner backgrounds. And so probably may at some point dominate the bulk of star formation in the universe at a very high redshift system. And here's another halo. And again, you can see that the accretion that's orthogonal to the flow is being disrupted. I guess I'm not going to go into the details of this, but you could show that 21 centimeters actually probing star formation and densities are quite a bit smaller than what we're probing with our deep HST observations. And in fact, I would claim that our HST observations are quite a bit, are probably incomplete at the highest redshifts. But we're talking about star formation rate densities of 10 to the minus 4 solar masses per year, which could conceivably be coming from these first halos. So solar masses per year per cubic meter. And so if you just go into the simulations and ask the question, how much gas can cool, has temperatures and densities such that it can cool within a Hubble time or a tenth of a Hubble time via molecular hydrogen transitions, then you find that that when there is this relative velocity, the factor of gas that can cool is of order a factor of a few smaller. And so this is you're creating homogeneities in your star formation, and the radiation background from these star forming sites could impact your 21 centimeter signal. And since I'm almost out of time, I'm not going to discuss that. And so what we find, again, we can use our simulations to calibrate predictions for the large-scale coupling, the coupling to large-scale nodes in the 21 centimeter signal. And we find that under some assumptions, the left panels are for X-ray heating, and the right are for the UV background fluctuations. The UV background coming from these first stars. That under certain situations you can have it, especially situations where a lot of your star formation is happening in these 10 to the 6 solar mass halos, you can have it so that you have a significant contribution to the signal that's coming from modulations owing to this relative velocity. And so, for example, in our most optimistic case, the black curve is from the relative velocity, and the dash is just from the tracing density. And the 21 centimeter signal is going to be a superposition of those two. And for example, at redshift 30, the effective relative velocity is quite a bit larger than redshift 20 because the relative velocity is redshifting away with time. And so in our paper, we discuss in detail what circumstances this relative velocity modulation could be an important contribution to the fluctuations. Okay, but that's it. And so most 21 centimeter experiments are targeting the signal from reionization, and I argued that these efforts will be mostly sensitive to the clustering of galaxies and ionization. So that's the first thing we're going to learn from these experiments. Some are targeting a strong absorption dip that occurs around redshift 40. And fortunately, we find that structural formation shocks do not erase this dip in contrast to the previous effort that investigated this. And could 21 centimeter fluctuations be enhanced by the supersonic streaming between of the baryons relative to the dark matter? We found that shock heating, homogeneous shock heating, was not sufficient to create large fluctuations, but that the modulation of X-ray and UV background fluctuations could potentially, under certain circumstances, enhance the 21 centimeter signal and give you larger BAO peaks. Okay, and so that's all. Thank you.
I learned recently that cold flows might be suppressed by the hydro. Ours was here.
So these are not cold
this is
flows.
much more. The shocks issue is in a much more linear phase.
Yeah, that's right.
But the issue arises to impress the hydro in that regime where.
So one of these is some of the hydro I'm showing you is with a Riemann solver, which gets these instabilities much better.
Right.
And we were not finding huge differences between Gadget and Enzo. And yeah, I actually watched Lawrence's talk yesterday so I think that's who you're referring to. Yeah. Yeah, so that's really, I mean, it's an interesting result. I mean, there's another thing that happens with the rainbow, which is that you you don't separate the phases as well. Like there's probably more artificial conduction, which can also be creating that. In a rainbow, yeah. But yeah, it's true that you don't have the color helmets instabilities captured as well in typical implementations of SPH.
So that's too non-nonlinear regime to be relevant for it.
It doesn't seem like it's relevant, and if it were, I think we would see larger differences between Gadget and Enzo. So this is just a comparison. It's hard to see, but this is our most massive halo in Gadget, and this is our most massive halo in Enzo. And yeah, it's true that there's some differences. They're not identical, but a lot of the features of the structure and these telemetry flows, which are maybe a high redshift analog to cold flows, are still present. So we're not finding huge differences. But yeah, we were worried that, I mean, it would have been crazy for us to just have gadgets and investigate shocks. And but it was also nice to have both methods to make sure that things were working properly.
In the paper, Dalal and Selbeck, they talked about the relative velocity effect. They suggested it might have an effect on much lower redshift observations of BAO from clustering of galaxies. What do your results on the early phase?
Yeah, well, I think that was more of a hypothesis, which is, so they said there could be some contribution to your clustering of galaxies that you're observing with BOSS and other redshift 0 and 1 galaxy surveys. And so their point was that so the phase of these peaks are different than the phase of the elevator traditionally looking for. So it would give you a bias. Now, and their argument was that even if the coupling is very small, you're looking for these, 10% fluctuations on your matter power spectrum, but you also want to measure these 10% fluctuations to 1% to do precision cosmology, and so you just need 1,000, part of 1,000 coupling to this. And so I think that's interesting to investigate, but I mean, it's not obvious how these really weak flows affecting very small halos at redshift 20 are affecting redshift 0 galaxies, which are much larger, much deeper potential levels. And so that coupling, as far as I know, could be 10 to the minus 6, 10 to the minus 8. And so I don't think they really looked into what the motivation is for it being 10 to the minus 3. But it could, as far as I know, it could also be 10 to the minus 3. So it might be an interesting exercise to go through.
Right. So you're not following these objects any further?
I'm not following them. Yeah, that's right. That's right.
Could you explain some of the ladder direction mention would impact the KFC signal from reionization, duration, scales?
Yeah, so there's also been a paper on this by I think Kendrick Smith was a co-author. That also, so this is a little bit, like you're not going all the way to redshift 0 galaxies for the KSC, but we think it's 10 to the 9 sort of mass galaxies or so that are ionizing the universe, and those are driving the topology of your reionization process. And so the KSC is really it's your ionization fraction fluctuations times your velocity. And so if these are also affecting the topology of the reionization process, they'll affect the KSC. But it's again not obvious to me that the 10 to 6 solar mass scale really is very important by the time you're producing enough ionizing photons to ionize the universe. Traditionally, you've been ignored when you're modeling reionization. And there I think you do want it to be an order unity contribution in order for it to significantly change the KSC.
And then in terms of the numerical conclusion of the shock heating, is there any sort of back-end calculation you can do to make sense of, except for how, why it's not, what way so there's such absorption relative to the event
I guess, I think there is an analytic calculation, which is that you can ask how much gas it has. If you make the ansatz that things are shocking at turnaround, and there might be a more sophisticated iteration, you can ask how much gas is at the turnaround radius with a sufficient velocity such that if it thermalized that velocity, it would heat up above the CMB. And there you find that at redshift 15, it's of order 10% of the gas, which is comparable to the 10% differences that we're finding. And so if you're only shocking when things are at turnaround, then that would be, I guess, the analytic calculation you could do. I guess you could also do a Zeldanovich type calculation where you ask how much gas in the universe has collapsed into sheets and filaments and halos with a sufficient velocity so that it heats up significantly. And that, I don't think that calculation is been done. But there might be something in the that you could do. So I think one of the worries was that these analytic calculations were missing, and this is the criticism that Gnedin had given that we're missing very weak shocks from flows that weren't turned around. But yeah, but I don't have a perfect analytic estimate. But it would be interesting.
With 10% at turnaround, according to what you're finding.
Yeah, that's right. That's right.
Great. Well, Phil, with the questions, let's thank the speaker and as usual.